and camera throughout the meet. And please don't try to share your screen. There will be a button for presenting your screen, but please don't use that. It will be an interruption to other participants when they are listening to our speakers screen. So please don't try to share your screen. And most of you may be familiar with the chat window of Google Meet. We are using the chat window for our question and answer session. You can type your questions, your doubts in the chat window, and our team will collect the questions for the question and answer session, and it will be asked to the speaker in the question and answer session by one of our student fellow. So that are the instructions. Let me repeat it once more. Please switch off your mic and camera, and please don't try to share your screen, and use the chat window in a good way. All other unnecessary talks in the chat window are strictly prohibited by the decision taken by the webinar committee. So please don't try to do that. And like I said, here is our 36th session of UL Space Club webinar series. It's on orbit dynamics. And we have a few more other programs in May month, and it will be declared by our Honorable Menda, our Kutisa. So he will announce that programs. And my friend Sriram is also here for giving an introduction about the topic. And for introducing the speaker, like I said, our Shri sir is here, and one of our student fellow will handle the question and answer session. And as you know, our participation for this for this session is very make me happy because we have 75 participants when we are starting this meet, and I think it's because all examinations are postponed, or the exams are finished so most of the students are free now, and we are very happy to have all of you here. Now we have around 80 participants in the Google Meet. So let me remind you the instructions. Please switch off your mic and camera, and please don't try to share your screen, and use the chat window in a good way. You can type all your questions and doubts in the chat window. We will collect the questions for the question and answer session. And if the time is available, you can ask the question directly. Otherwise, our student fellow will ask the question to the chief speaker. So let me welcome my friend Sriram to give an introduction about the topic and our webinar session. So Sriram, are you there?
Yes, Varnat. Let me first go to the winners of previous webinar quiz. I think that will be better. So
the last two webinar quiz results were not published. We were published it in our social media platforms, but I noticed that few students didn't notice that. So we would like to announce it once more in this program. So Sriram will announce the quiz winners, and he will announce today's quiz also. So Sriram, go.
Oh, okay, Varnata, thank you. I would like to announce the results of the UL Space Quiz 35, which has been held after the last webinar. The third position is grabbed by a 9th grade student from GVHSS Pune, and he is Muhammad Ayan VM. Congratulations to you. The one who reached at the second position is a astronomy student from University of Bern, Switzerland. He is Thomas Lam. And finally, the first prize holder, the cash prize winner sponsored by Center by Nature, is a 4th grade student at Jawahar Vidyalaya, Tamil Nadu, and he is our Harish V. It's a huge pleasure to us that a student from a reputed international institution participated and won our webinar quiz. And it also gives much happiness while knowing that students who nurtured by UL Space Club also reached with them in the leaderboard. Hearty congratulations to all winners and participants. Well done, folks. Today also we have webinar quiz, as Varnatan mentioned. The quiz link will be posted at the end of the session via chat box. It will be only activated after the vote of thanks. The quiz will be based on your general knowledge on the respective topics and also about the things discussed in that session. The fastest and accurate answers by yours will be crowned, and a special surprising invitation is waiting for you, as we mentioned a long back ago. So that will be we are planning great events in the upcoming months. So you can expect more from us. So be ready and best wishes from the side of UL Space Club. So on that note, Shailesh sir, can I move to the formal introduction of the topic?
Yes, you proceed.
Thank you, sir. A warm good afternoon to all once again. We are here after an interim of a month or so. Thanks to Varnatan for providing the instructions. I cordially invite all the veteran scientists, teachers, UL Space Club organizers, students, and all other participants to the 36th session of UL Space Club's webinar series. We, the UL Space Club, is a foundation under the umbrella of Uralangal Labour Cooperative Society, stands for enriching and flourishing the scientific aptitude of students, especially in space field. Within a short time span of 3 to 4 years, we conducted many great offline events before the COVID. And exactly in May 2020, in the context of the pandemic era, we began this new journey called the webinar series, and it's going incredibly well for the past 12 months. Yes, for a year. So, grand programs are scheduled to celebrate the first anniversary of our webinar series. That detail will be shared with you before the webinar concludes. That will be done by our chief mentor, Ike Kutisa. So, with that being said, let me move to the official obligations which has assigned to me. Today, in the 36th session, we have Shri Subramanian Bhuminathan as the lead speaker on the topic orbit dynamics. While thinking about the topic, it is simple to understand. Taking an example, just as the different seats in a theater provide different perspectives on a performance, different Earth orbits give satellites varying perspectives, each valuable for different reasons. Some seem to hover over a single spot, providing a constant view of one face of the Earth, while the others circle the planet, zipping over many different places in a day. There are essentially three types of Earth orbits, which will be very familiar to us because, as Kutisa said, PJ Bhatt take a very good class for us. I think from Calicut University, if I'm right. So that details are known to many of us. The high Earth orbit, medium Earth orbit, and low Earth orbit. Many weather and some communication satellites tend to have a high Earth orbit furthest away from the surface. And satellites that orbit in a medium Earth orbit include navigation and or specialty satellites in such way, and designed to monitor a particular region. Most scientific satellites includes NASA's and our Earth orbiting system have a low Earth orbit. As I mentioned in the write-up of this webinar, in the study of dynamical systems, an orbit is a collection of points related by time evolution. The points of the orbit which will be a subset of the phase or the state space of the dynamical system. Satellites are pitched into this well-defined arena. But which laws govern the orbital motion? How satellites disturb the orbits? Well, I'm not the right person to talk about these questions. We have an expert in flight dynamics who is currently working as a scientist at URSC in Bangalore with us to cover all matters related to this topic. It's our privilege to have you here, sir, and gladly welcome you to the 36th session of UL Space Club webinar series. Namaste, Subramanian, sir. And after that, thank you, sir. Thank you, sir. And after that, we have all core team members of webinar committee here to give you the instructions when it's necessary. And our moderator is, as usual, Shajil sir, the one who controlling and developing our platform in each and every session. And he will gonna introduce our respected speaker too. Our chief mentor, Ike Kutisa, the former director of ISRO, who is the backbone of the whole activities of Space Club, is here with us. The whole webinar family, including the eminent scientists all over India, will be with us in this session too. And one of UL Space Club fellow will handle the Q&A session after the talk. The one who plays a major role in connecting us to UL, Damodaran sir, will be with us for taking the vote of thanks session. I hope so. Otherwise, Adil is here to do that. Right now, this webinar is recording and streaming in YouTube by our member, which I mentioned now, Adil Krishna. So all set, good to go. Without any further delays, I invite the moderator, Shajil Sir, to take over the session. Welcome, sir.
Okay, thank you, Sriram. And we are so happy to see that you become a little bit more academic in this orbit dynamics. That's the thing we expect from the students, your part, because when you get a hint, you search for that and what's the things and what's the orbit dynamics and its theoretical parts also considered. So really wonderful. Sriram, is a great congratulations to you making a special environment or room for this talk here. Today we are sitting here in the 36th program of your Space Club. I still remember the day, the May 23rd, 2020, we started this program. At that time, the Google Meet was our platform, and it was not so familiar with all the participants and its presenters. And the COVID, the pandemic made the whole community, the educators and the entire world technically more literate, and the things become more easy than ever before. So even though we are struggling with this and enjoying the opportunity we got, and by that we evolved a lot in these sessions. UL Space Club started in 2016 under the leadership of E.K. Kutisar, former director of ISRO. And we continued these things in our annual space camps. Physical meeting was there. When it was a abrupt end to all these programs in 2020, and really it was an opportunity to evolve all these things. And when we go now, when we are sitting here in the 36th session, we are completing an annual cycle here. The next, already stated, May 23rd, we will celebrate by the students. They themselves present their development and their views in front of in a forum of all the scholars, educators, and scientists of UL Space Club who are continuously supporting us. And the 35th webinar was with spacecraft mechanism. It was also from a great scientist from UR Rao Satellite Center, Murli sir, and he presented it well, and it was all the secret about the spacecraft mechanism here. Today, we are dealing with the orbit dynamics, and we know it's a pure application of physics and mathematical principles, that already the basic principles learned by the students, and it's an application that makes the wonder. Still, we are using this, even though in today itself we are in fear of the fall of the Long March 5B, the satellite, the rocket from China that may fall, even Australia, Africa, India, that we are under threat even today night and tomorrow morning that may happen. But we are calculating all these things based on these principles, basic mathematics and physics that we are doing here. So anyhow, the UL Space Club made a wonderful environment for our students in this very difficult pandemic era of 1 year. And I would say that we could do a lot of things. Then even if there was no such a condition, we could not accomplish these kind of things for our students. The first thing is that we started this UL Space Club just for curious and just providing some information. Now it's evolved to some other realms, and it's an academic platform for our students too. In previous year, we started a program called Race to Rank 1, through which we intended to guide the students to their academic achievements. And in this year, this UL Space Club started that program under the mentorship of Dr. Jyoti Basu, and he was also associated with UL Space Club through a webinar, and is a long friend of our E.K. Kutisar, and he is guiding around 15 students for their higher ambitious examinations like KVPY and JEE, through which we expect these students will cross these barriers of these privileged barriers of JEE and KVPY, and they will reach in the Premier Institute of India. So we are nurturing, actually, really we are nurturing these students, and And we extend the support to the other students also if they are willing to join with us, and Kuti sir will make a formal declaration of these things. So all these program going on voluntary basis, we have made a zero budget economy and for the development of students. And one more thing we added here that I will present, sorry Subramanian sir, I have to present the UL Space Club website.
Sure,
We
sure.
have a website here, it's very active now, and we are updating a UL Space Club team is updating is continuously. And before I go to the formal introduction of our chief guest here, please let me present that our website for 1 minute, sir.
Yeah.
Please permit me, sir. Okay. This is the UL Space Club website, and in every day, in every program, we are making this kind of an ad window will be there. Today also, it's also done in the previous day. Today's speaker and everything is given in that website, and it contains a lot of information, what we do, what are our objectives, and these are the tabs there. I request all the members to go through, make use of these wonderful website, and in that we have our the chairman of ULCCS and the chief mentor, and who is the whole heart of this program, E.K. Kuti sir and Jairam sir, and all these people are mentioned there, and all our missions and all our achievements are already included, and there is scope for membership also. And so it's a wonder for us that when we are declaring the UL Space Club quiz program, I wonder that some of the winners are from outside India. So that means we are globally, there is no limitation, there is no regional or any kind of continental limitations are there. We are open to them, and anybody can join with us, and we can create a good academic environment for the students under the umbrella of the space science and veteran scientists of ISRO and working scientists, and we can explore the world of science through this program. So we are proudly presenting this our website here for your future reference. Then without taking much more time, we have a great person from UR Rao Satellite Center, Subramanian Bhumanathan sir here, and I know he's a mathematical background with him, even though he's an engineer, and he's so interested, and he's applying his ideas proudly for our network, because the orbit is in that orbit, all our investments and all our expectations are going on there, and a lot of basics are given by our veteran scientists here. PJ Buddies are already given a lot of lectures to our students, even though we are now overwhelming or over flooded with our capacity. In the 99, that's the number of participants. Okay, it exceeded 100 now. So I could feel some kind of rush in joining the program. That's the thing. So happy to declare that. And before taking much more time, I want to introduce the great scientist from UR Rao Satellite Center, Subramanian Bhumanathan sir. He is a holder of master's degree in aeronautical science, and he became part of our prestigious ISRO in UR Rao Satellite Center in the year 2000. And he was worked in the Orbit Dynamic Division of Flight Dynamics Group at UR Rao Satellite Center in the field of orbit determination that involves evaluation of tracking data obtained by ranging satellites. The development of satellite state vector prediction software, satellite orbit determination during orbit maneuver phase of satellite mission, during launch using which maneuvers are planned to raise the orbit of the satellite to geosynchronous altitudes. That means he's able to control all the things when a launch is over by the rocket is there, and it's the life of that satellite is in the hands of these this scientist and his team. His work also involves the development of flight dynamic software system FDSS for the GEO mission, which is an integrated software executive that runs the full set of about 60 GEO flight dynamic programs in a controlled environment with proper directions to input access, configuration file management, result generations. This flight dynamic software system is employed for daily operations of current 30 spacecraft that have been made operational after guiding into geostationary orbits. We could happily and proudly say that the life of the satellites are in the hands of these kind of proud scientists of his and in addition to these achievements, he contributed to the journals and some international conferences, with more than 10 publications. So we are proudly presenting these great and simple men from UR Rao Satellite Center who accepted our invitation for nurturing the students to the high altitudes. So I welcome this great scientist of UR Rao Satellite Center to deliver his wonderful and interesting presentation to our students and those who are watching this program through YouTube channel also. That's happening simultaneously here. Those who couldn't join here can join with us through the UL Space Club YouTube channel that's available. Anybody can join here. And in addition to that, this group is flourished with the presence of a lot of scientists like P.J. Bhatt sir, then Subramanian sir, and Jairam sir, and a lot of known and unknown famous person to me. And I welcome all of you and the student community also to this program. And proudly, I welcome our guest, Subramanian Bhumidathan sir, to make his presentation. Welcome, sir.
Thank you very much, sir. Thank you very much for that great introduction and all the words which you have told. It is really a pleasure and honor to be in this platform to meet all of you. So I will begin my talk. Respected former director of ISRO, Shri Kuti sir, respected distinguished scientist and former Deputy Director of Mission Development Area in URSC, P.J. Bhatt sir, who under whom I have worked for a long time in URSC and who has guided me in many ways. I have a great honor to meet you in this platform, sir. Thank you for being here. And Shaji sir, with whom I first started interacting yesterday, and it was such a pleasure to meet him. And I also thank him for giving an introduction to the activities of the Space Club, which Kuti sir also had told me earlier. And I also want to thank Varun, who was also coordinating with me earlier to schedule this and go ahead with the progress of this meeting and this talk. And I also wish to address my student friends who have joined in a good number. And I also have my respects to all the other distinguished ISRO scientists and other distinguished dignitaries who are watching this program. I thank all of them a lot, and with this, I think I can start my lecture. Thank you very much, and now I will go ahead with my talk. I will now switch over to the presentation mode. I think is the presentation visible, sir? No.
No, you have to present it once. Okay, sir. It's okay. It's there. Okay.
Is it visible, sir? Now, can I go ahead?
I think you have to present it once more. That's good, sir.
Okay.
Yes, sir. Then the students can easily ping that screen.
Okay. Present it once more. Okay, it has come, sir. It has come. Okay, one more request to the participants. Don't try to present or use your mic like that. You will get the chance to ask questions. Then only you will be permitted to uh, ask the question, intervene. Otherwise, we'll be forced to make some other actions. Okay, please cooperate with us. Okay, so please continue.
Sir, now my presentation is visible?
Yes, it is visible.
Yes, sir,
Very
it's
visible.
okay, sir. It's okay.
Good,
It's okay.
good.
Yeah. So now I switched over to the next slide. Is it now visible?
Yes, yes, it's moving charts. The
Okay,
slides are visible. Okay, sir.
Yeah.
It's okay.
So, dear friends, now in this talk, we will see in general how a satellite which is launched by a rocket, how does it remain in orbit? So, just if you shoot a stone or if you shoot a bullet or something, it just comes back to Earth. But how are satellites remaining in orbit? So, we will be discussing about these, and we'll be seeing some of the aspects of these in the course of this talk. And next, we will also be seeing the types of satellite orbits into which a rocket can launch a satellite. The orbits can be of different types and different sizes. Why different types of orbits are chosen, and what are the advantages, and how we are making use of that in our regular day-to-day lives. So what is the intention of these kind of different kinds of orbits, and how and how these kinds of orbits are taking place, and what is the purpose and how we make use of them. So these kind of topics also we'll be dealing in the course of this lecture. So first we will see how we go into an orbit. The first point here says, this is a quote by Douglas Adams, who says, "The knack to flying lies in how to throw yourself at the ground and then miss." That is, you are throwing yourself into the ground. Whether it may be simply like you are standing on a stool and then jumping, or you are standing on a ladder and then jumping. So you just throw yourself on the ground, but you should know how to miss. So this we will see what he means by that. So that is the knack of going into orbit. What is really going on is you are always being pulled towards the earth or any other central body from which you are trying to launch yourself, or you are trying to launch the satellite. So when you are doing that, you should have enough sideways speed. That is the third point which is shown here. I hope all students and all participants, I request them to follow the pointer mark. I hope it is visible. So that is the only way in which I can direct you to which point I am talking on the slide. So now this third point says, if you have enough sideways speed, you will miss the earth as it curves away from beneath you. That is what is called as getting into orbit. That is, you are falling, but you are not hitting the earth. For that, you should have enough sideways speed. So this we will see in this particular slide, where we are talking about something called as Newton's mountain. This is not like some Mount Everest or something like that. This is Newton's mountain in the sense it is a concept, Newton's mountain, because what is happening here is, imagine yourself launching a succession of rockets upwards at increasing speeds. Suppose you're standing in this mountain here at the top, and then you are launching yourself sideways. So when you launch yourself sideways with a low speed, then you will be falling somewhere in this point, which is very close to the mountain. If you launch yourself sideways with a better speed, then you will be reaching somewhere at this point, which is called E, which is named E. And if you are able to launch yourself with a greater speed, then you will fall further away to this particular point. So in this way, if you are able to launch yourself with enough force, then you will never hit the earth and you will get into orbit. that was what which was being told in the previous slide. You should launch yourself sideways with such a great speed that you keep missing the earth, and the earth will be curving and moving beneath you, but you will never hit it. So this is the way, this is the process, this is the target which we should try to achieve, to launch something, any object. It may be a stone, or it may be a bullet, or it can even be a satellite, so that it doesn't hit back the earth and it rotates in space in a particular curved path, which is called as a trajectory or an orbit. So these are the general broad classifications which we will be seeing in the course of this topic. The governing laws of motion to stay in orbit, definition of orbital elements, how do we define an orbit? So how do we define orbital elements? Then the reference frames for orbit and artificial satellites. How are reference frames formed, and how are they coordinated, so that we can define an orbit or an artificial satellite's orbit. Then the forces that perturb orbits and orbit transfers, how to transfer from one orbit to the other, and the types of orbits and their classifications. So these are the major topics which we will be covering during the course of this talk. So firstly, we will see what are Kepler's laws. These are the foundations of orbit dynamics. What are Kepler's laws? The Kepler's first law says the orbit of each planet is an ellipse with sun at one of its foci. That means you have to draw an ellipse which has two focuses, two foci, and then if the sun is in one of the foci, the planet moves around the sun in an elliptical path. That is very, very important. See, this has a great significance, this very first law, because let us see, if you wake up in the morning, and then if you stand on a seashore, and if you see the sun rising, you will see that it will be curving upwards, and then you will start imagining that it is probably moving in a circular path. You will not say that the sun is moving in a square, or the sun is moving in a rectangular path. That will not strike you, but just by mere observation, some common sense may tell you, okay, maybe the sun is moving in a circular path. So this was the way which our previous generations and our earlier folks were thinking, that all the motions were happening in a circular path only, because that is the simplest form of shape which comes to mind when we see these motions just with our naked eye. But it was Kepler who monitored all these planets' movements, and then he came to a great conclusion which had very significant impact on the whole orbit mechanics, and I can even say the way of life today, that the planets are moving around the sun in elliptical paths and not circular paths. And earlier, again, at first sight, it will look like the sun is moving around the earth, the stars are moving around the earth. I'm saying just by a naked eye observation. But it was Copernicus who first said the sun is at the center and the planets are revolving around the sun. But he said they are revolving around the sun in circular paths. And the jump from circle to ellipse happened by Kepler. So that was his greatest achievement, based on which the whole orbit mechanics, the space mechanics, and whatever we have to do with space depends on that. And how he came to that conclusion? For that, he had to thank a person called Tycho Brahe. Tycho Brahe was a German person, and he's a very rich man. He was a nobleman, and what he did was he had very powerful telescopes and very good instrumentation, and his job was to sit out in the nights and then monitor which planet is coming where and at what time. So he had so much of data. He accumulated so much of data, and that data was merely observations. Which planet is located going in which direction at time t1 at 9:30. This planet was at this position from the horizon. At 9:31, the other planet was at this position from the horizon, and at this right ascension at this angle. So like that, he had voluminous data, and Kepler was lucky enough to get hold of this data. And once he had all this data, so his job was to mark all these points, and then he was never able to fit a circle in these points. And that was the reason from which he tried to fit an ellipse, and he came to the conclusion all planets are revolving around the sun in an elliptical path. And the greatness comes here because the ellipse in which the earth, for example, rotates around the sun is almost circular. It is such a close ellipse to the circle, it is very, very difficult to identify that it is actually going in an elliptical path. But on the other hand, if you look at an object like Pluto or Uranium, Uranus, it would have been a bit easy, and at first sight itself, you can say it is an elliptical path because the ellipticity was high. But with respect to the closer planets around the sun, the difference between the circle and ellipse was so small, it was obvious, like what others were thinking, that it should have been a circle. But it was Kepler who was able to distinguish that it was not following a circle, but an ellipse. So here I want to bring my attention to the student community, the power of instrumentation, the power of electronics, the power of observation. So there may be some minor disturbances or some minor deviations from the common sense which we have, and we should be able to spot that and then say something looks different. That may not, whatever others say may not be right. So could it be like this? So that kind of a proposition should come from the student community. In that way, we can make some progress. So in that way, he was able to come to the conclusion that the planets are revolving around the sun in an elliptical path based on the observations made by Tycho Brahe. So this is something which we take for granted today, but at his time, it was a great finding. And in the same way, today, when we are in this 21st century, we know a lot of things, and there may be something which we can further do to improve the science or the technology. So that should be our intention, like how Kepler did in those days, and how the other scientists have improved upon the observations. So that is regarding the first law. And coming to the second law, the line joining the sun to the planet sweeps out equal areas in equal intervals of time. So this is again based on the observations which he had from Tycho Brahe. So I invite the attention of the audience to look at the second rectangle, which is below this. So here you see the sun and a planet going around the sun in an elliptical path, and you have shaded regions. So that is the areas which we are talking about. So what Kepler did was, because he had the observations of Tycho Brahe, he will simply trace the mark the point of a planet at say at time t1, and then at say 1 hour from t1. Suppose this is at t1. This is the other point is t1 plus 1 hour. So he will mark this point, And then again after 1 hour, where is the planet? So that point he will mark. So suppose the planet is here, he will mark a point at that, suppose this point is T3. He will mark a point T3 plus 1 hour. So that will be this point. So let us see these 4 points. So this is T1, say. This is T1 plus 1 hour T2, which comes here. And this is T3. And this point is T3 plus 1 hour, which is T4. So now he has marked this region as this shaded region, and he calculated this area. And this region from T3 to T4, he shaded this region and he calculated this area. He found this area was equal to this area. So in that way, what is the conclusion that we can come from this? So just by seeing this pattern, now some thinking is required now. Here the time is maintained same in equal intervals of time, that is mentioned in point number 2. So it is T1 plus 1 hour. Here it is T3 plus 1 hour. But here if you see, you look at the curve which the spacecraft has covered in this region. In 1 hour, it has covered from T1 to T2 this amount of arc on the ellipse. But here from T3 to T4, again, though it is 1 hour, it is able to cover only this particular segment of the arc. When you compare this arc with this arc, it is very obvious this is small. So in 1 hour, a fellow here is able to travel to here, covering so much distance. That means he is traveling very fast. In the same 1 hour, that fellow is able to travel from here to here only. That means he has become a bit slow. And he, at the other end, he has marked, this is the area which equals this area. And here, if you see the arc which is covered, this is the smallest. So in this kind of a elliptical pattern, when the planet is moving, this particular point is the closest to the sun, which is called perigee, which I'll come into those details later on in this talk. And this is the farthest distance from the sun, and this point is called the apogee. This is the perigee and this is the apogee. So when the planet is near the sun, it travels very fast, and the speed at which it travels is the minimum at the other end. So this is the most important conclusion which he came to again based on the observations. So he just had Tycho Brahe's observations, and the first point he found was it is traveling in an ellipse, and he also found in the elliptical path, when the planet is closest to the sun, it is traveling at its highest speed, and that speed keeps on decreasing, and when it goes to the other end, it becomes minimum, and again as it keeps coming closer to the sun, it slowly increases and it reaches the maximum speed here. So at the perigee, you can say the velocity of the satellite or the planet about the central body is maximum, and the velocity or speed at the other end, which is called the apogee, is minimum. This was possible because he was able to plot this, he was able to measure the areas, and he did a lot of experiments with the data which he had in hand, and he came to this important conclusion. This is also very important, which you have to note down, so that when we come to the later slides, we will be getting back to this. Now, coming to the third law, which says the square of periods of planets are proportional to cube of their mean distance from sun. So let us say, let us represent a period by the letter P, and then the mean distance from the sun, let us say it is D. This law simply says P squared, square of the periods, which is P squared, is directly proportional to D cube, cube of the mean distance from the sun. So this was again, what he did, he will calculate the time taken for this planet to complete one rotation. That is the period T of the planet. Or if it is a satellite around the Earth, how much time it takes for the satellite to complete one rotation. or to complete one orbit, that is P. And then the mean distance from the sun, because the distance from the central planet, central body is not equal because we are not in a circle. So what is the mean distance you have to calculate, and then D cubed you have to take. So that is directly proportional to P squared. This again came from the, because he knew what are the orbital periods of the planets, and he also knew the distances from the sun. Based on that, he was able to come to this conclusion, which is also very important. So, so dear students, my friends, this particular slide is very, very important. I have explained to you the 3 laws. I'm telling it is very, very important because when we go further discussing about the satellite orbits, etc., again we have to recollect this. So you can mark somewhere that you have to keep this in mind. Some of you may be knowing this already, but we will pinpoint to this particular Kepler law number 2 or Kepler law number 3 when we go to the other slides. Okay. Now these are the orbit terms. Now we are coming. Let us say a rocket has launched a satellite into orbit. Now, how do you define an orbit in mathematical terms, or how do you say that? How do you represent an orbit, or how do you put an orbit on paper, and how do you deal with the mathematics of an orbit? So how do you represent? So these are the things which you are going to see now. As I told you earlier, apogee is the furthest point of the satellite or the planet in the ellipse. The perigee is the nearest point to the central body. The period is the time taken to complete one particular orbit. The inclination is the angle of the orbital plane relative to the equator. All this I'll be showing you in figures in the coming slides. And eccentricity is the out of roundness of an orbit. Out of roundness of an orbit. So these particular terms, we will see their definition through this figure. Here, a central body is drawn, and you should assume a satellite or a planet rotating about the sun, or a satellite about the earth. So the orbital elements are defined in this way. The first one is A, which is denoted by small letter A, semi-major axis. We have an ellipse in which this is called the major axis, and this is called the minor axis. And the half of this major axis, that is from the central point to this point, or from the central point to this point, is called the semi-major axis. So this is the first term in which an orbit is defined. The second one is the eccentricity, which I told in the previous slide, is the out of roundness. What is that out of roundness? If something is round, then you say that it is actually centric. Suppose this is the body and something is moving about it in a circular path, then you should say it is a centric orbit. But if it is not moving in a circular path, and if it is moving in an elliptical path, that means the distance of that object from the central body is not the same. Sometimes it is near, sometimes it is slightly far, sometimes it is very far. Again, the distance comes closer. In that way, it is not centric. It is eccentric. It is like telling Jawaharlal Nehru was our former prime minister. He was our ex-prime minister. So in the same way, it is not centric, but it is eccentric. So that is the way in which this particular term was coined. This is pure English. So in that way, that is the definition of the eccentricity. And in mathematical terms, we know, some of the students can recollect, it is the ratio of the distance of a point which moves, distance of a point from a fixed point, which is called the foci, and the distance from a fixed line, which is called the directrix, from which we know that we can form ellipse, hyperbola, parabola. The students who are there in higher classes, they can recollect that. And the planets, as told by Kepler, it is moving in elliptical paths, which has an eccentricity. That ellipse has an eccentricity, and it is not moving in a circle. So this eccentricity we have now seen in three ways. It is like, see, suppose a person is mingling with everybody and he has a lot of friends, then we say he is highly dynamic and he is centric. A person who does not mingle with a lot of friends, he keeps aloof and he sits in a corner. But suddenly, if he wants something, he comes and asks his friends, and again he goes back. This kind of a person, we may say he is not so very open. Maybe he is an eccentric, you may say. In the same way, this planet is not always following a centric path. Sometimes it moves away, sometimes it comes near. So it is that planet is an eccentric fellow. So that is purely English point of view. Then from mathematics point of view, it is the ratio of distance from a fixed point to a distance from a straight line, directrix. That is pure mathematics. There you will see E is equal to 0 is ellipse, and less than 1 it is E is equal to 0 is a circle. Sorry, E is equal to E is less than 1 is ellipse. E is equal to 1 is parabola. E is greater than 1 is hyperbola. Students who are there in higher classes, they can recollect this. That is pure mathematics. There you start solving x squared by a squared plus y squared by b squared is equal to 1, etc. All you might have done a lot of sums. That is pure mathematics. But what Kepler did, there are some telescopic observations. Some planet is coming somewhere in some time. It is coming at some elevation, at some right ascension. He has marked a point, and he is able to fit an ellipse to that. That is science and technology. So this from English, you go to mathematics, and then you go to science and technology, and how we are applying that in our day-to-day lives. So a lot of meaning and a lot of research is there in one single word, eccentricity. Next, we come to inclination. So now I direct your attention to the figure below. So here, this is the central body, and this is the orbital plane, which is mentioned here. That means the satellite is moving in an orbital plane in this direction, and this is let us say this is the Earth, which is moving around the sun. This particular plane is called the this is the equatorial plane, which is the central plane of the Earth, and this is the orbital plane in which the satellite is rotating about the Earth. So if you see the angle between this orbital plane and the equatorial plane, that is called the inclination. If the orbital plane is further tilted, say here it may be, I may be some of the order of some 45 degrees, and if you further tilt it, I will be 60 degrees. If you further tilt it, I can be 90 degrees. Or the other way, if you are able to tilt it this way, from 45 it can come to 30, up to 15, and it can coincide with the equatorial plane itself, the orbital plane. At that time, you should say inclination is 0. So that is the definition of inclination. That is the angle between the orbital plane and the equatorial plane of Earth. It is this angle. This is inclination. Now, this is called as argument of perigee, the fourth parameter of an orbit. The fifth one is the right ascension of ascending node. So, dear students, now don't be, these terminologies may be very cumbersome for you to understand in the beginning, but slowly you will get accustomed to it, though it looks like somewhat Latin and Greek. So first we will see what is this particular Greek symbol, which is capital omega in Greek, is called the right ascension of ascending node, and its unit is degrees. So it is also an angle, but what angle? Suppose from the center of the Earth, this is the equatorial plane, you have an axis which is called x-axis. This x-axis, how it is defined, that we will come to see that in the future slides. So now you have to assume we have a coordinate system in which the center is at the center of the Earth. In this coordinate system, which is a three-dimensional coordinate system, you have x-axis, you have y-axis, and then you have z-axis. In this three-dimensional system, and you have to look at in this orbital plane. Suppose this is the center of the Earth, and this satellite is moving in this direction. So when it is crossing the equatorial plane, it has gone into the northern hemisphere of the Earth. These regions are in the southern hemisphere of the Earth. It comes to the equatorial region and it has gone to the northern region. The point at which it comes from the southern hemisphere to the northern hemisphere and cuts the equatorial plane, that point is called the ascending node. It is called the ascending node. And if the satellite's direction of motion is this way, it goes here, reaches a point, and comes here, and then it comes from the northern hemisphere to the southern hemisphere. So this point is called the descending node. So this is the ascending node from south to north. It goes and comes back the other opposite point of the diameter. It is coming from the south, north to south. That is the descending node. So when this is called ascending node, this particular point joining to the center, what does this line make from the x-axis? That is called as capital omega, or the right ascension of ascending node. So students, this may be a bit complicated to understand at the beginning, but you can just assume this right ascension of ascending node gives an indication at which point the satellite crosses from the south to north. So in a simple way, you can assume that way. And the actual angle is from the x-axis to the point where the satellite crosses from the south to north. That is called the right ascension of ascending node. Now coming to this fourth point, which we have, which I skipped earlier. This is the argument of perigee. This is again represented by a Greek letter, which is small omega. So now what is this? We have seen here in the Earth, the satellite goes in an ellipse, and somewhere it is at the perigee, somewhere at the apogee, the nearest point and then the farthest point. So this also you assume to be an ellipse, and you assume that this is the point where the perigee happens, and the other end is the apogee. That means this is the closest point to the Earth, and this is the farthest point. Once you find the closest point to the Earth, you join it with the Earth center. You will get one line, and you know the place where this line, where the satellite goes from south to north, is there. From this particular line where the perigee occurs, that angle is called small omega. So this is again maybe a bit complicated to understand at first hand, but you can take it in a simple way, that the small omega gives an indication where the perigee occurs in the orbit. So that is the representation, and it is called as small omega. And once the small omega is defined, we come to the sixth term, which is called theta, or which is true anomaly. So here this orbit is represented this way, and the satellite keeps going around. At some point it is at perigee, at some point it will be here, at some point it will be here. So what is the to locate the satellite in the ellipse at a particular instant, that is called true anomaly. So that is the true anomaly, is the angle between the satellite at a particular position and its angle with the perigee apogee axis. See, this is the perigee apogee axis, and suppose this is the point at which the satellite is there. What is this angle? That angle gives an indication of the position of the satellite in the ellipse at a particular point. So this particular angle is called the true anomaly. So to recapitulate, we know what is semi-major axis. That is quite simple. Ellipse has the minor major axis, and you take the half of the major axis, that is semi-major. Then eccentricity. Eccentricity says how whether it is a circle or it is an ellipse or if it is something else. That is the second point. Then the inclination. It tells the way in which the orbital plane makes an angle to the equatorial plane. Then the fourth thing is the right ascension of ascending node, where the satellite goes from north to south or south to south to north or north to south on the other end, and then the argument of perigee, where the satellite is at the closest point towards the central body, and the true anomaly, that is the exact point in the orbit of the satellite. So here, in general, we can say we have 6 orbital elements. The number of orbital elements is 6. It is like when we want to mark a point, suppose we draw an x-axis and suppose we draw a y-axis, and if we mark a point here, that will be represented by xy. And if it is a 3-dimensional cube, then if you mark a point somewhere in the cube, that is xyz. And the velocity of the object in each direction, xyz, will be dx by dt, dy by dt, dz by dt. This is for students who know calculus, some very fundamental calculus, or it is x dot, y dot, z dot. So xyz position, x dot, y dot, z dot is the velocities in the respective directions. So xyz and x dot, y dot, z dot is one of the ways in which you can represent an orbit, and that xyz, x dot, y dot, z dot is converted into these 6 orbital elements, because when we look at these orbital elements, we will know the kind of orbit which we are in, the place in which a satellite is. All these things we will come to know if we put the orbital elements in this way, rather than telling in terms of x, y, z, x dot, y dot, z dot. For example, if a satellite is here, you can find out what is the xy from this point. In 3-dimensional place, you can find the point of this satellite in xyz from let us say the center of the earth. That is possible. And the velocities can also be measured in each direction, and you can find out x dot, y dot, z dot. So you can say my orbit is xyz, x dot, y dot, z dot. For example, it is 50, 100, 200, 5 kilometers per second, 10 kilometers per second, 15 kilometers per second. It is like 50 kilometers, 100 kilometers, 200 kilometers, 5 kilometers per second, 10 kilometers per second, 15 kilometers per second. This is my orbit. And if another satellite is going in a different orbit, you can say it is 100, 200, 300, 10, 20, 30 kilometers per second. That is another orbit. But when you give numbers like this, you will not have an idea that what does that 50, 100, 200 or something, will it give me the, does it directly tell me whether the satellite is at perigee or whether it is at apogee, or what is the inclination of the orbit? All those things you will not be able to get if you give the numbers in terms of x, y, z, x dot, y dot, z dot. But if you convert this x, y, z, x dot, y dot, z dot into this a, e, I, omega, omega, theta, then it is easy for us to visualize how the orbit is in space. So that is the ingenious way in which our scientists have deliberately coined these 6 orbital elements, instead of simply telling it in abscissa form, that is the xyz, x dot, y dot, z dot, or in terms of abscissa, we should say, instead of the Cartesian coordinates, it is represented in this form, so that it will be easy for us to visualize. And it is also important because tomorrow, when we have to deal with maneuvering a satellite from one orbit to the other, we should know what is perigee, what is apogee, etc. So that is important. So students, you can you have to make a point. You have to note down the point that an orbit is represented by Cartesian coordinates x, y, z, x dot, y dot, z dot. And the other way of representing the orbit is a, e, I, small omega, capital omega, theta, which is a function of x, y, z, x dot, y dot, z dot. For example, you imagine I is equal to, say, some formula like tan inverse of z by x, something like that. If you have z by x or something like that, you will be able to get I. And omega and a will be equal to some square root of x squared plus y squared by z squared by 2. I'm just giving some examples, but there are very complicated formulas in which you can get a, e, I, omega, omega, theta from x, y, z, x dot, y dot, z dot, which are the Cartesian coordinates. And we should thank our scientists, our earlier scientists, our earlier astronomers, etc., who were able to visualize this kind of a system so that it makes it easy for us to understand an orbit rather than putting it in simply Cartesian coordinates. So that is the importance of this particular slide. So we should know what is AEI, this omega, omega, theta, which represent an orbit. So this is the way an orbit is represented. Now, out of these 6 elements, the first 2, A and E, they are called shape parameters. We will see why shape parameters. We were talking about eccentricity, and we also know that it represents the out of roundness. That is what is called out of roundness within quotes. So it is not round, but this is a smaller ellipse. This is a somewhat slightly bigger ellipse. The second one, which is in between, the dashed line. The third line is somewhat a bigger ellipse. So what does it show? The outer fellow is much flatter than the intermediate one, and this intermediate dash is much flatter than the first ellipse, which is shown in thick line. So the ellipse shows what is the bulge of the orbit. The satellite is moving in this way, whether the orbit is thinner or it is obese. What is the bulge in the orbit? So that is given by this eccentricity, where it is shown here. This is a much flatter ellipse. This is somewhat bulkier, where the obesity is more, and this is much bulkier. So here the inner ellipse has high eccentricity. The outer ellipse has low eccentricity. Here, the semi-major axis from here to here is A1. The semi-major axis from here, the center to here, that is the second ellipse, that is A2. The third ellipse is much bigger. So that center will be here. From that point to this point is A3. So this one, which shows different kinds of A, semi-major axis, A1, A2, A3, gives an idea of how big or how small is the orbit. This is a smaller orbit. This is slightly bigger orbit. This is an even bigger orbit, because and that is represented by the semi-major axis, which grows bigger. The higher the semi-major axis, the bigger the orbit. So that is the size of the orbit. That is with respect to A. And the shape of the orbit, whether it is thin or whether it is fat, that is given by the eccentricity. So the semi-major axis gives the size of the orbit, how small or how big. The eccentricity gives the bulge of the orbit, how thin or how flat, or whether it is circular. So that is regarding the first 2 orbit parameters. The other 4, which we will see in this particular slide, they are called orientation parameters. This particular slide, this is the third parameter, inclination, which shows whether the orbit is close to the equator or whether the orbit is perpendicular to the equator, etc. So that is the angle which we are worried about. And then here, this is the capital omega, which is the ascending node. From the x-axis, whether it is ascending at 30 degrees or whether it is going very far away from the x-axis and then ascending. So the place at where it is going from the southern hemisphere to the northern hemisphere, how far that is from the x-axis. So that is the angle which is given by omega. And then the small omega, which is the argument of perigee, it shows from the node, where is the perigee happening. That is, see, this is the nearest point, this is the farthest point. If the ellipse is here, the perigee is here. If the ellipse is here, the perigee is here. If the ellipse is here, the perigee is here. How far this perigee is from the ascending node. So that is the angle given by this. And this was the true anomaly which I was showing. The position of the satellite at time T1, T2, T3 from the perigee. So from the perigee, you are measuring this angle, which I am showing through the pointer. Now it is mu1. Mu is the Greek letter used for true anomaly. And here it is mu2, and here it is mu3. So if mu is 0, it is perigee. If mu is 180, it is apogee. So all these 4 parameters in this set of 6 elements represents orientation. Orientation in sense, angle. How far it is away from the equator, how far away it is from the x-axis it is ascending. from the ascending node, what is the angle which is made by the perigee, and from the perigee, what is the angle made by the position. So it goes sequentially. What is the orbital plane inclination with respect to equator, and then in the equator where it is crossing from south to north at this angle or this angle or this angle, and once it has crossed, where is the perigee happening? Is it happening at this angle or this angle? That is small omega. And once you have found out the perigee, from the perigee, where is the satellite? At this point, or this point. So all these angles represent the direction or the orientation, or it is all in degrees, which is angle, that is orientation. The first one represents the size, how big or how small. The second one represents the eccentricity, which is how flat or how bulgy is the orbit. So these are the 6 orbital parameters which help us define an orbit. Now going further, now we come to the orbital dynamics. Here we all know that Newton's second law, which tells that the force is directly proportional to the rate of change of velocity, and it acts in the direction of the change. So from that we derive the constant of which is mass. F is equal to ma. This is a well-known equation which is represented here in vectorial form. And the apart from the Newton's 3 laws of motion, Newton formed one important universal law of gravitation. That is this is the one which is based on the story of the apple, which says the force of attraction between 2 bodies is directly proportional to the masses m1 and m2. Suppose you have a body m1 and suppose you have a body m2. There is a force of attraction between them which is directly proportional to the product of the masses m1 and m2, but inversely proportional to the distance between them. The distance between them here is r, and it is inversely proportional to the square of the distance between them, which is r squared. So based on this, we have a universal gravitational constant, which is g. So this is the law of universal gravitation, and this is the second law. And by equating these two f, here you have an f and here you have an f, and by cancelling out m2, you can derive this formula, which gives an idea about the acceleration experienced by body 2 towards body 1, which is g m1 by r squared. This is the acceleration of the body 1 to body 2. So this is the way in which the orbit will, the satellite moves around an earth, or the planet moves around the sun. So that is based on this particular principle, product of the masses inversely proportional to the square of the distance between the 2 bodies. So this is the fundamental governing equation of motion, based on which the orbit dynamics is formed. Now coming to the reference frames, because we are talking about that x, y, z, x dot, y dot, z dot. So for that we should have a frame. That was what I was telling earlier. So here the earlier astronomers, you have to imagine the earth, and this is the equatorial plane. And if this equatorial plane is extended infinitely into the cosmos, so this is the extended equatorial plane, and that is called as the celestial equator. And the perpendicular to the celestial equator through the north pole, that is called the north celestial pole. And the angle from this particular line, this is called the x-axis, and it is also called the vernal equinox. I will tell you why it is called so in the future slides. And from this angle, whatever is the position of the object is here along the equatorial plane. That is called the right ascension angle. The object is here, and you project it onto the celestial equator and measure how far it is from the equator. The object is here, project it into celestial equator, and how far it is from the x-axis or the vernal equinox. That is called the right ascension in general. And then from the equatorial plane, how much it is from the celestial equator. That is called the elevation. This is called the elevation from the equatorial plane. So this is one of the celestial frames which our earlier astronomers used. And this is called as the ECI frame, or the Earth-centered inertial frame. Here is where we come to the definition of the vernal equinox. So I was talking to you earlier in the previous slides about this particular x-axis from which we are measuring this capital omega. That is the place where it crosses from the south to north. What is this x-axis or the so-called vernal equinox? So here, dear student friends, now you have to have some imagination. You have to imagine in your thoughts. It is like see, now you have two planes. One is the Earth's equatorial plane. So first you imagine that the Earth's equatorial plane, and you please recollect that the Earth is tilted at an angle of 23.5 degrees, roughly 23.5 degrees. It is in a tilted way that the Earth is revolving around the sun, in a tilted way. But the Earth's center is moving. You for a moment you imagine that this is the sun and this is the Earth, though it is not shown that way. The Earth is moving around the sun in a circle, and the center of the Earth will be covering a particular curve. That particular plane is called as the ecliptic plane, and the Earth is moving in a tilted way, and the equatorial plane is making an angle of 23.5 degrees with respect to the ecliptic plane. And now one important point which all of us can understand: if you fold a paper, it will form two planes, and those two planes will be meeting in a straight line. So that is the edge, that is the fold or the edge which is formed when you fold a paper, the edge which is formed. So it is for you to imagine and then understand that two planes meet in a straight line. So that particular straight line is called, that particular straight line will always point to a distant star which is in a particular constellation. The planets are revolving around the sun in the solar system, but we have the 12 zodiac signs like Libra, like for example Pisces, Capricorn. We have the zodiac signs, and we have one particular constellation in which you have a star, and this particular the line of intersection between the equatorial plane and the ecliptic plane always points to that particular star. That particular star is called the first point of Aries. Aries is also, you can recollect, is one of the constellations which is far light. We have to talk in terms of light years, which you may be knowing. The time taken for light to travel in 1 second or in 1 year. So that is a huge distance, and these constellations are so very far away. The Earth orbit around the sun, which is at a radius of 150 million kilometers. The mean distance between the Earth and sun, that 150 million kilometers is nothing when you compare the distance of that Aries constellation from our solar system. So as the Earth keeps moving around the sun, the equatorial plane keeps making a straight line at the that is the line of intersection between the two planes. But wherever the Earth is, that x-axis will keep pointing in this direction, and that is the direction towards that distant constellation, which is and that particular direction is called as the x-axis. So that is how that x-axis is fixed in the Earth's center here. So that is the definition of the x-axis in the cosmos. So you have to imagine equatorial plane, ecliptic plane, the line of intersection which points to a distant star, and that line of intersection always maintains parallelly even as the Earth moves. And here you have the Earth center, and that particular direction is called the x-axis. And the z-axis is quite easy to understand. It is the axis which is perpendicular to the equatorial plane and passing through the North Pole. That is the z-axis. And once you have formed the coordinate system's origin, which is the center of the Earth, O, and then the x-axis, which we have defined based on the line of intersection, which is a bit complicated, but it requires some thinking. And if you are able to, if you go and think over, you will understand that and this z-axis is the North Pole line. And once you have formed the center and these two lines, you have to get the third line, which is perpendicular to both the axes, that is y-axis. So the y-axis forms the right-hand triad. So first you form the center, you define the origin of the coordinate system, which is center of the earth. Then you define the x-axis. Then you define the z-axis, and then you complete the coordinate system by drawing the y-axis, which is perpendicular to both x and z. So this particular frame, which required a lot of thinking to form, which we now take it for granted, the way in which they have thought about this is really fantastic, unimaginable. But now this is the way the x, y, z coordinate system is formed, based on which, as I told you earlier, the orbits are defined as x, y, z, x dot, y dot, z dot, and k, e, I, omega, and true anomaly, theta. So this is the way the coordinate system is formed, the origin is formed, the Cartesian coordinates are defined, and then the other set of orbital parameters are defined. Now, this is the there are other ways in which the coordinate system can be formed. This is one of the coordinate frames, which is called as Greenwich coordinate frame. This is written here, Greenwich coordinate frame, in which the world map is shown here. This is the African continent. India is somewhere here, and this is the place somewhere where England is situated. And in England, somewhere around London, you have the place called Greenwich. And the longitude of that Greenwich, this is the longitude, that is the 0-degree meridian, which we all know. So when you make a point from the center of the earth along the equatorial plane, where the Greenwich meridian cuts the equator, that you can define as x. And then z is as usual along the North Pole. And once x and z and the central point is known, you can complete the y by making it perpendicular to x and z. So this is the Greenwich frame based on the particular place called Greenwich, which lies in England. And this is also this we cannot miss, because all of us know about the GMT, Greenwich Mean Time, and we also know that we are 5.5 hours earlier to the Greenwich Mean Time. That is when in India we have so many longitudes here in India, but the central longitude is 82.5 degrees, and that is 5.5 hours earlier to the Greenwich time. So because of that importance of Greenwich, there is one frame called as Greenwich coordinate system, which is based on that particular location, Greenwich. But suppose you want to say why Greenwich? Why not Bangalore, or why not Trivandrum, or why not Chennai, or why not Hassan? Suppose we think like that. So that is also possible. That is called as topocentric coordinate frame. In that, whatever is your point of interest, from that point of interest, you hang a pendulum. If you hang a pendulum, you will get the northern direction. Northern in the sense, the point directly above you in the direction of gravity. So that will give you the northern point, which is this particular axis. And from your longitude, you draw a line which is tangent to the meridian, which passes through the North Pole. That is the second axis. Once you get these two axes, you can complete the coordinate system by taking the other axis, which is perpendicular to these two axes. So whatever is your point of interest on Earth, so that is topocentric. You fix that as the center. That is topocentric. That is anywhere on Earth. And you form the northern direction, the north direction, and then the other direction which completes the coordinate system. And you have your own coordinate system based on your own center. This is the topocentric coordinate system. So here, these are all different. There are even more multiple ways in which you can form the coordinate systems, and each are required for one particular purpose. And the another important thing which we should note is, when you know something in one particular coordinate system, you can get the coordinates in the other coordinate system by a process called as coordinate transformation. So by that coordinate transformation, you can switch over from one coordinate system to the other. Now coming to this another important topic, this is we can say that we are going to some kind of a chapter, we can say a new chapter in this particular talk. This is about orbit perturbations. So here when I say perturbations, all students, you can just imagine, I just want to bring to your attention, suppose a satellite is launched by a rocket, and that satellite is kept in a perpendicular orbit. That is, it goes from north to south. It is exactly at 90 degrees to the equator. And suppose we leave the satellite in that particular orbit. Now we have a question on hand. Will that particular orbit remain like that forever? Because the rocket has been fired and it has injected the satellite, and the satellite is going and it has done a very perfect job. It is 90.0000 degrees from north to south. That orbital plane is making an exact 90 degrees to the equatorial plane. Inclination is 90 degrees, and we leave the satellite in that orbit and then just relax. So, and we always shall we think, now the question is, shall we assume, is it correct to tell that the satellite will always maintain that particular angle towards the equatorial plane? So that this was studied by the scientists, space scientists, and those involved in space mechanics, orbital mechanics, and then they came to the conclusion, after the launch and you have put the satellite at 90 degrees, if you go and look at the orbit, say after some 1 month, that angle is not at all maintained. That angle is totally different. It may be even a very significant difference. So you have just put the satellite in that orbit and you have not done anything to it. But where has the satellite gone? It has not reached Earth also. It has not escaped somewhere also. It is there in some orbit, but it is not in 90 degrees. How it has happened? That means there are some disturbances to the orbit, even if you don't do anything. So student friends, now please look at one concept. Suppose a satellite is in orbit 1, say O1, and if you want to change the satellite orbit to another orbit, say O2, you have two options now. Without doing anything itself, the satellite can come from O1 to O2, or the other way is the satellite has a propulsion engine in which the propellants are loaded. They are all chemical propellants, or they can be ion propellants, or it can be a variety of propellants in which propellants are there. By firing that propellant, that engine on board the satellite is fired, and you can change the shape and size of the orbit and then come from orbit O1 to O2. So you have two choices. One is artificial. What you have made some engine, you have fixed that engine in the satellite, you fire the engine in some way and then get from orbit O1 to O2. The other way is you don't do anything, but suddenly you see that orbit O1 has gone to O2. But so these are the two kinds of ways in which the orbit of a satellite can be changed. But the orbit of a satellite getting changed on its own, that is, I won't say on its own, by a way other than firing the engine, that is because of orbital perturbations. And the disturbances to the orbit is called by the term perturbations, within quotes, perturbations. Perturbations means disturbance to the satellite's orbit by some other means, not by the mechanical way in which an engine is fired, a man-made engine is fired on the satellite. In some other way, the orbit has changed. That is due to nature, and that kind of disturbances are called perturbations. And when I say nature, it can be because of the asphericity of the Earth. You note this capital A, asphericity of the Earth. This capital A is important. Asphericity of the Earth is one of the ways in which the orbit gets disturbed. Aerodynamic drag disturbs the orbit. Solar radiation pressure is another concept which disturbs the orbit, lunisolar force, which is a fourth kind of disturbance on the orbit. So in essence, instead of making a disturbance to the satellite through a man-made object like an engine sitting in the satellite, the disturbance on the satellite due to nature, like Earth, here luni means lunar, that means moon, then sun. here again we have sun, and this aerodynamic drag has got to do with atmosphere. So due to these particular reasons, the satellite may get disturbed in its orbit, and it can reach the other orbit. And this particular topic is called orbit perturbations. So here I have shown an image of an Earth here. So in general, all of us can recollect one famous photograph, because now we have so many satellites going around Moon, Mars, Venus, etc. One of the famous photographs taken by a satellite around Moon on the Earth. Many of you might have seen. It is a blue Earth, and from that distance, if you see, it might almost be a perfect circle. It looks like a perfect blue Earth. But when scientists were measuring with made a lot of measurements from the center of the Earth, they formed this kind of a curve. So this also many of my student friends might have studied in their classes, that the Earth is not a perfect sphere. It's almost like an orange. It's flattened at the top, and it is bulging in the along the equator. And this particular shape, which I have shown you in particular, because this is again to bring to your attention the importance of electronics, the importance of instrumentation, the importance of measurements, the importance of precision, the importance of accuracy. All these things come into picture. Whatever you see, for you, by looking at naked eye, something may look circle. But when you want to be precise, it is not circle, it is an ellipse. And then you assume something is going along in the same way, but you see that the orbit is getting disturbed in a very small way. For that, again, you require very precise measurements. Again, you think that the Earth shape is a circle, but it is not circle, it is just flat, and it is bulgy in the equator. But again, if you make further precision, you see it is simply not just like in the equator. There are so many different places in so many different points from the center. So this is called the sphericity of the Earth. That is, the sphere is the Earth is not a perfect sphere, but it is not. It deviates from the spherical shape, and that is called sphericity. And we will see how this is affecting the orbit of the satellite. So in this particular place, this is the orbit of the satellite, which is shown in a red line. And you imagine this particular strip as also an Earth, but which is detached from the perfect sphere. Here is the bulge. So because of this bulge, the pull of the satellite, when it is here, it will be in this direction. The bulge of the satellite pulls the satellite in this direction. So in this way, the orbit of the satellite gets disturbed, because we know that the laws of motion tell that it is directly proportional to the masses. Suppose there is a bigger mass somewhere here, and the mass is somewhere lesser, and the distance is lesser here, and the distance is more here. The force experienced by the satellite will be in this direction here and this direction here. And in this way, the satellite orbit gets disturbed because of the Earth's sphericity. And here, when we come to the here, we should also note one more point. Suppose a question is being asked, which is the suppose I say, dear students, you can go to any place on Earth, but you please find a place on Earth which is closest to space. When I say space, you have to keep going up and up and up and up in a vertical direction where you don't find any atmosphere, say at some altitude of 200 kilometers and above. That particular region, let us say, that is called the vast space expanding into the cosmos. So if you have to go to some particular point on Earth, And then you can say at this particular point, I am closest to space, then what will be that particular point? Here, I can just give you one hint. We all know which is the tallest point on Earth from the Earth's mean sea level. It is Mount Everest. Suppose you say, if I go and stand on top of Mount Everest, then I'll be closest to space. If that is the answer, then that may or may not be the right answer. That much I can tell. You can ponder over it. Now, coming to this particular slide, here here again, I request everyone not to be baffled by these equations. Here, I just want to bring to your attention, especially when I am talking about orbit perturbations. There are two equations which I have shown. Here it is nothing but capital omega dot. We all know what is capital omega, right? Ascension of ascending node, and when I put a dot over it, it is d omega by dt. It is nothing but how the right ascension of ascending node is moving with respect to time. As I told, the orbit is not fixed. Somehow it is getting disturbed. And when it's getting disturbed, that right ascension of ascending node, that particular angle from the x-axis, that is also changing. How it is changing with respect to time. For that, again, by measurements, they have formed this kind of an equation. And the second equation is how the small omega dot. This is related to the argument of perigee. That is the position of perigee from the node. So how that is also changing. So in an orbit, A is changing, E is changing, omega, small omega is changing, capital omega is changing. But with by constant observation, you can form this kind of an equation in which, so now in this particular slide, we are dealing with capital omega dot, variation of capital omega with respect to time, small omega with respect to time. And in the right hand side, if you see, it is a function of semi-major axis A, the orbital inclination I, the eccentricity of the orbit E. In the same way, small omega dot, if you see, it is a function of semi-major axis A, the orbital inclination I, the eccentricity E. So when you have an orbit by which you define AEI, omega dot, omega, capital omega, and then theta. When you know that orbit, you know AE and I. And once you know AE and I, you will be able to find the way in which capital omega is changing and small omega is changing. So this particular slide is to just tell you the power of observations, the power of monitoring, the power of instrumentation, and the way in which the forces have been measured, the way in which the orbits have been observed, and then these kind of equations can be formed. And it is not simply writing down equations for the sake of equation and then telling I have done good mathematics. When you are actually talking something on your phone, or when you are talking about, say, some India-Pakistan war, let us say, for example, in that kind of a condition, how these kind of equations are going to help. So that is the significance of these equations, where you are putting things into practice. So how these play a role in whatever important things which we see in life. It may sound too bombastic, but it does have an effect which we can see. So this particular the way in which I showed the orbit being disturbed by the pull here and the pull here shifts the orbit in this particular direction. In this way, the right ascension of ascending node keeps changing, and the variation of ascending node with respect to time I had shown in the equation in the previous slide. And now coming to the other perturbation, which is the atmospheric drag, which I have shown here. We are now talking about this second concept, aerodynamic drag. What does this aerodynamic drag do? So this aerodynamic drag is a function of, here again I have shown an equation. Here again I will tell you just the simple facts. This is a drag force experienced by the satellite which is directly dependent on the square of the velocity. This is v squared, and it also depends on the density of the atmosphere, which is rho, and it also depends on the area, this particular area of the satellite, which is facing, which is perpendicular to the velocity vector. In that way, we can say this area is the area of the surface of the satellite. Suppose the satellite is in the form of a cube or cuboid. One particular face of the cube will be perpendicular to the velocity, the direction in which the satellite is moving. And that particular area is A. This is the velocity of the satellite. This is the density of the atmosphere through which the satellite is moving. And based on this, you can find the drag force. When you say drag force, it is nothing but when we are moving in a car or when we are moving in a plane or whatever movement in the atmosphere, we naturally see the resistance force from the atmosphere or from the wind in the opposite direction. It acts in the direction opposite to the velocity. That is nothing but the drag, and that depends on these three factors. So how it affects? So when a satellite is in this green line, and this is the Earth, and this particular shaded region is the extent to which the atmosphere extends from the surface of this surface of the Earth. So here we have something called as the intermolecular distance. At the surface of the Earth, it is densest. It is like roughly some 1.225 kilogram by meter cube. That is the atmospheric density at the sea level. As you keep going higher, the molecular distance between the air particles keeps on increasing, and the density keeps on decreasing. After certain height, the atmosphere ends, and the drag experienced by the satellite will be minimal. So suppose a satellite is in this green line, and suppose it enters the atmosphere. Once it enters the atmosphere, it encounters resistance. And if this atmosphere had not been there, it would have traced that green circle and it would have again reached here. But because the opposite, the push which is experienced by the satellite in the opposite direction, in this way, here it gets retarded, it gets decelerated. So instead of following the green line, it is able to get up to this height only, which is the red line. Now again, after coming to the red line, after again it enters into the atmosphere, here again it faces resistance. After facing resistance here, it is not able to reach this height here in this red line, but it is able to come, its height has reduced to this blue line. So because of this atmospheric drag, if you leave the satellite in this green line and assume that it will always be in this green line, it is not so. It is being disturbed by one particular disturbance, which is called aerodynamic drag, and that aerodynamic drag is because of the Earth's atmosphere, and that atmospheric effect is nothing but it is reducing the altitude of the satellite. So if I get into some physics of it, I hope students will be able to catch up with me. It's quite simple. Total energy is equal to potential energy plus kinetic energy. So a satellite, when it is here at this particular altitude from the Earth, potential energy in a simple form, we can say mgh, and it depends upon the altitude. So because the altitude is higher here, you can say it has a higher potential. And when it comes here, and here it is at the apogee, which is the farthest point. At the farthest point, the potential is high, but the velocity is less, we know, because we have seen at apogee, velocity is less, and kinetic energy is half mv squared. Kinetic energy is less, potential energy is more. As we come here, as this is the perigee point, and it is closest point to Earth, where velocity is highest, but the altitude has become less. So here, half mv squared, kinetic energy is high, potential energy is low. And once you come here, it is not able to reach this potential. That is the point. It is not able to come back to its original potential, which it had as a consequence of its altitude. That altitude has been disturbed or dragged by this fellow, which is nothing but the atmospheric atmosphere over Earth. The atmosphere which gives life to us is actually disturbing the satellite. So this potential keeps on coming down, and finally what happens, the this apogee perigee is here. Here the apogee has come to this point, and finally it will keep on coming, and finally it will come and hit the earth, and that is the place of re-entry. As in the introductory speech, Shaji Sher, he actually made a very timely observation, and he will also be happy to know about this now. He was talking about a Long March 5 and its body, which the Chinese agency has simply left it like that. It is really a very huge. It is almost like 21 tons in weight, and it is simply drifting in the atmosphere. Nobody to ask, and where it will come and hit the earth. That is also not known. But the only satisfaction for the community, the humanity here is the atmosphere over the earth, which disturbs the satellite and creates trouble for us, also helps us because of the friction with which the body will enter the atmosphere. The heat will be in thousands of Kelvin and thousands of centigrade. That metal or whatever it is, that will get burnt and only ashes or some few particles will come and hit the earth. But still the damage is possible, and what they are telling us, it is under 1%. So though what the Chinese have done is not legally right, luckily what the expectation is, because 70% of our earth is covered by oceans and seas. First of all, it will not hit a landmass. That is point number one. So the danger is less, but the danger is there for the ships and the animal kingdom in that particular place. But on the other one is, even if it hits, it may be small fragments which may cause a slight damage. But whatever it is, little damage or more damage is damage, and it has its own legal consequences. And there is a huge world community working on it, how to reduce these kind of things, and that can be summed up in one single word called as debris. DEBRIS. This simple word has a lot of consequences. There are a lot of committees, lot of space organizations working on it, because we have not only made the earth an unsafe place by littering on earth. Now we have littered all over the space, especially the Western community, the Russian community, and the others who have launched a hell of a lot of satellites. And some of you may know now the ongoing launch of Starlink satellites, thousands of satellites. It is going to create havoc, and the future is going to be really tough. So this is one important topic which all my student friends, they should try to understand the basics of it, and they can follow the news, and and uh, they can choose a very good career in this particular topic. It has great consequences for our the satellite communications, because everything depends on the satellite today. This particular topic is of great significance. So we should understand the fundamental physical principles of this. And the third one is the solar radiation pressure. This is when we talk about solar radiation pressure, we can think about two kinds of forces from the sun. One is about the one kind of force. Here, please underline the word kind of force from the sun. The first kind of force is radiation. What is the second kind? I will come to it later. Now, many of you may be aware there are sunspots on the sun. The sun is a huge chemical factory. No, I should not say chemical factory. It's a nuclear factory, and it keeps on. There are a lot of explosions going around there, and it emits radiation. It is either through light or through heat. These light particles or heat particles, when they come and hit the surface of the satellite which is moving in one particular orbit, it experiences a force, and it changes the orbit of the satellite. So now our topic is the how these orbits, satellite orbit is getting changed. So the satellite radiation pressure on the satellite changes the uh, orbits shape or size or whatever. This is one kind of. The other one is uh, the perturbation due to the gravity. The sun also has gravity. The sun is so massive. This is the kind number 2. I told underlined kind. This is the second kind. The gravitational force of the sun and moon, that also disturbs the orbit of the satellite. The first one was the radiation, either because of the electromagnetic radiation from the sun, moon, or the reflection of the sun's radiation on the earth and moon on the satellite, that disturbs the orbit. That is kind number 1. Then the second kind of force, which is gravitational force, which is different from the electromagnetic force, and this gravitational force disturbs the satellite orbit. Why that happens is, see, this is the north pole of the earth. This gets tumbled around like this because of the sun's gravity, and this north pole rotates in a conical way and covers one full circle in 26,000 years. This is called precession. And because of this, when the north pole is here, the equatorial plane is here. When the equatorial plane is this way, that intersection line, the vernal equinox x direction is one way. Now, as this north pole keeps on changing, the equatorial plane also keeps on changing. The line of intersection with the ecliptic plane changes, and the x-axis vernal equinox also changes. So this is one of the reasons why the x-axis, which was pointing at one particular constellation of as I told you, Aries, keeps on shifting. Now it has gone to Pisces constellation. So this is one of the effects. Now in this cone, there is a small deviation in this form. This is a sinusoidal pattern, and this has a period of 18.6 years, and this is caused by moon's gravity, and this is called as nutation. So so this precession and nutation causes a wobble of the earth. This is like in an understandable way. Suppose a top, the spinning top is a good example. Suppose it is perpendicular, and the top is spinning, and if you give a slight nudge in this way to the spinning top, it'll start wobbling like this. In the same way, the Earth's not Earth, which is rotating like a top, because of the sun and the moon, it gives a nudge, which I told, towards the top, and it makes the North Pole to rotate like this. So this kind of disturbance by the sun and the moon, which disturbs the Earth's motion itself, again disturbs the orbit of the satellite. This is the fourth kind. So we have talked about the Earth's asphericity, the atmospheric drag, which disturbs the satellite orbit, then the sun radiation pressure, which is electromagnetic kind of force, then the gravitational kind of force from the sun and moon, which again affects the orbit. So these kinds of orbits affect these kinds of forces perturb the satellite's orbit and disturbs it, and we have to keep on monitoring that. By that is why we have a lot of ground stations of the earth. We have a lot of antennas. We keep sending signals to the satellite and receiving it back, which we will not be able to do if we just keep quiet and then assume that the satellite orbit is going to remain the same. Now now coming to another important point, life of the satellite. We all know, suppose we are going in a car or a scooter, we fill up petrol. Suppose the petrol gets over, all we have to do is go to a petrol tank and then fill it up. Now we have spent millions of dollars, crores of rupees, and then we have launched a satellite into orbit by taking painstaking methods. Launching a rocket is not simple. Anything, see, suppose you have to climb Mount Everest. Somebody will ask, do you think, so suppose something is very simple, like say going from our hall room to bedroom by walking. You will say, you can walk from the hall room to bedroom easily, you don't require any great physics for that. Don't think it is rocket science, they will say. Don't think it is rocket science, they will say. That means rocket science is so difficult, which is unimaginable, which is the most difficult thing. And anything which is so simple, we will say, don't think it is rocket science. That is English, because there are so much complications in launching a rocket. If you make 1 millimeter difference in the manufacture of one propellant feeding pipe, some 1,000 crore rupees will be lost. So rocket science is so difficult, and after doing that, you have launched a satellite with some propellants, and once you have launched the satellite, you cannot go to a petrol station to refill that propellant in that engine, and you can keep on changing the orbit according to your wish, and the life of the satellite will be endless. So that is not the case. The propellant is going to be spent when you have to do some maneuvers and when you have to change the orbit, and when you keep on spending the propellant, sometime the petrol is going to be over, and then it is going to be uncontrollable, and it will just be moving with respect to gravity. So when that is the case, the intention of all space scientists and all space technologists, how to save every single fuel drop of propellant on the satellite. So ISRO has a lot of expertise in this. Our former scientists, our senior scientists of ISRO, in the very development stage, they have formed through their experience of multiple launches, how to save even every single drop of the propellant. By that, we have now come to a stage where we can maximize the life of a satellite. So here, why I am talking about all this is, I told here, look at this particular graph. Here, the satellite is, let us say, launched in an orbit A, which has an inclination I, which that inclination is less, which is some 30 degrees. The second one is orbit B, inclination is more. Let us say that inclination is 40 degrees. Third orbit is C, that inclination is, let us say, 50 degrees. So 30 to 40 to 50. So now this particular orbit of A will trace this particular region on Earth. You have spread out this Earth, which is 3-dimensional, into a 2-dimensional paper, and if you project it, that satellite orbit will be along A. This satellite orbit will be along B because the inclination is more, so the latitude is higher, so it will reach slightly higher latitude, that is B, which is in between curve. Then the C has gone further, the latitude is further north, so it will be able to go in this particular orbit C. So you have 3 different kinds of orbit, A, B, and C, at lower latitude, higher altitude, and you have something called as the beam, the electronic beam from the satellite, which is pointing towards the Earth, and the stations here will be able to receive the satellite beam. Let us say it is a TV beam. The region in this particular area covered by A will be able to receive the satellite signal. In B, the region covered is more. So the more region is covered by this particular satellite, so it is more effective. The region covered by C is even more, so it is an even more effective satellite. So to make the satellite signal reachable to more, we are making that satellite more effective to humanity. And the point here is to go from A to C, how to go? So you have to change the inclination. One method, simple method, is you have petrol on satellite, simply fire it, change it from A to C. So, and you have achieved your target. You have covered more region, and you have made the satellite more useful. But the penalty which you have paid is you have spent the fuel. Now the life of satellite has come, say from 15 years to 10 years. So how to avoid this? So that is where the equations which I have shown you earlier, that capital omega dot, small omega dot, all that plays a role. If you are able to allow the Earth, the Moon, and the Sun, and the atmospheric drag to do this job of moving a satellite from A to C, instead of firing an engine, instead of spending petrol, then you have understood that equation. You know what A is, you know what E is, you know what I is, and you know how I will change just because of you have understood the gravitational pull of Sun and Moon. And once you have understood that, you don't fire that petrol, you simply allow the nature itself to do this job, and you increase the life of the satellite. So that is where the technology comes into picture. First, understanding the forces which act on the satellite, and then now you apply your technology, and you think that the satellite which you have launched with a lot of cost, which so many so many dollars or so many rupees per kilogram of this is very important. All space scientists think to launch 1 kilogram of payload on the satellite through a rocket, how much fuel you have to spend. So that is very important. So to do all that, you have to make use of the orbit perturbations itself. Using that, if you are able to do, you can save petrol. So now coming to the other types of orbits, this is an inclined orbit. This is an equatorial orbit where inclination is 0. This is a polar orbit where inclination is 90 degrees. In a polar orbit, the Earth is rotating from west to east. A satellite is moving from north to south. So the full Earth is covered. In the equatorial orbit, if you are able to put one satellite such that it is moving in the same rotation rate as the Earth, then you can keep it at a particular point on Earth, and you can keep receiving the signals from the satellite over this particular point. See here, this orbit covered is 24 hours. The Earth rotates around itself in 24 hours. When this angular rate is equal to this angular rate, you can keep the satellite about one particular point, and you can get this geostationary orbit. This is where you have to go back to Kepler's third law, which says p squared is equal to d cube. So if the period should be 24 hours, what should be d? That is 36,000 kilometers. So this particular orbit was imagined by Arthur Clarke. He only first stated, if you put it as 36,000 kilometers using third law of Kepler, you will get 24-hour orbit, and using 3 particular satellites, you can cover the full Earth. So here again, dear students, just note down. See, Kepler, he was in 17th century. Clarke was in 20th century, and after 3 centuries, he simply made use of some 300-year-old law, and we now have hundreds and thousands of geostationary satellites. So like that, if you keep on thinking about some earlier laws of earlier scientists, you will also be able to come up and frame one particular orbit, and you can also get that orbit name, your name for that orbit. For example, Varun's orbit, like this is called Clarke's orbit. You can have let Varun, if he ponders over, and if he is able to think one particular orbit based on some particular law, and if he is able to give one useful orbit, that will be named as Varun's orbit. So this kind of possibilities are still there, even though the inventions have been made much earlier. Sir, I'm going a bit faster now because I have much exceeded the time, I think. Sir, is it okay? No?
Sir, it's okay, but actually time is 5 o'clock now, sir. So the work is very interesting. I also sitting there, but when we consider the time, it's 5 p.m. Okay, sir. Okay, you can.
Okay. Okay, I'll just quickly go through. I have a few slides only. So this shows the geostationary satellite covering this particular area. This is 1/3 of the Earth. So this is the other third. This is the other third. So in this whole Earth will be covered. And this is the geostationary orbit, which is at the 36,000 kilometer altitude. Here I have shown the number of satellites in one particular year, which are occupying this particular slot, and the crowded satellites in this region, in this region. Here it is over USA. Here it is over Europe. Here it is over Chinese. Here is where we have concentrated satellites in this particular belt. This is the geostationary satellite at 36,000 kilometers, where it remains stationary over a particular point of Earth. And this is another kind of orbit, which is called Molniya orbit, which is used by Russians. They launch satellites in such a way that satellite stays more number of time over Russia and less number of time in the southern hemisphere. Here it stays more number of time, means the velocity is less. That is, the apogee will be here. It will travel very fast in the perigee, where they cannot get the signal from Russia. They cannot get the signal from this point when the satellite is here. So they will allow that satellite to travel very fast here, and they'll put the perigee here, the apogee here, where it will be very slow, and they will keep getting signals here. This is called a Molniya satellite, where the inclination is 63.5. That IE63 is again derived from the earlier formula which I showed. And this is the sun synchronous polar orbit, which is nothing but this polar orbit. If you have to take photographs on the Earth, if you come back to the same region, and if you take the photograph, the illumination conditions should be same, the exposure should be same, the sun from the lighting condition from the sun should be same. So the inclination of the orbit should be at one particular inclination, so that you keep taking photographs of the Earth at the same illumination conditions. This is very important, even from defense point of view, from our army and military operations point of view, even from agriculture point of view, where we can monitor crops, etc. And these are nothing but the ways in which this particular graph shows how the satellite is communicating to a station. This is the station, and here is the tangent. When the satellite is moving from here, when it crosses this this tangent, it will be visible to this particular station. That is called acquisition of signal, or AOS. And when it comes to this region and goes below this tangent, it is LOS, loss of signal. So you have the time between this and this, between which you have to download your data from the satellite. So you should be able to know the orbit of the satellite correctly for this. And you should know here is the sun, and here is the Earth, and this is the satellite orbit. When the orbit and the satellite gets behind the Earth, it will get into an eclipse. So here the problem we have is the solar panels on the satellite will not be able to generate power, and you have to switch on the battery. So for that, you should know the orbit of the satellite correctly, so that you'll be able to predict when it gets into eclipse and when it comes out of the eclipse, and how long the battery should function. So this is an importance of how precisely you know the orbit. And this is an orbit transfer. This is the orbit in which the satellite is launched. You want to go into a bigger orbit. So when the satellite comes here, you make a firing. You get into an intermediate orbit, elliptical orbit. When you reach here, again you give a firing, and you get into a bigger orbit. So this is the way the propellant is fired in the satellite, and we lose some satellite life also, but that is unavoidable. And here we keep doing station keeping maneuvers. This is called we spend 3 meters per second per year to keep the satellite within a particular longitude, and this is called north-south station keeping, where the inclination of the orbit has to be maintained within a particular band, for which we have to give a velocity of 45 meters per second. Here again the question of spending propellant and reducing the life of the satellite. But these are all ways in which the satellite is kept in a particular region where you feel it is beneficial. And this is the way in which interplanetary missions are conducted. This is the Earth and this is the Moon. You want a satellite to get into Moon, so you keep firing the satellite here. When it gets to the perigee, you give a small push. The kinetic energy is added and the potential is increased. It comes here. When it comes here, again its velocity is very high. You give again a small nudge. It'll go into higher ellipse. Like again, when it comes very fast, and here it'll going at a tremendous speed. Again, you give a firing here. It will keep going here. And once it reaches somewhere near Moon, it will get into Moon's orbit and it won't return back to Earth. And here again, you can fire the engine and then get the correct orbit which you want around the Moon. This is a very fundamental way in which I have shown in which interplanetary missions are conducted. So this is the way in which we go from one planet to other. So with that, I come to a conclusion of my topic. Thanks a lot for all of you for the patience with which you have heard me. Thank you very much.
Thank you, sir. It was really interesting. And at the beginning, you started with the Kepler law and basics of gravity, and gradually you developed these things. And I am interestingly watching the pedagogy you applied here as an academic in perspective. I could, as a teacher, I felt like that, and it was really interesting. And we only considered about the time, but we already fixed the time. That's the 5 p.m. So it's only 10 minutes. But the 10 minutes was so valuable, sir. The information was so valuable. available. And so we are so happy to keep your lecture in our YouTube channel, and that will be a repository, knowledge repository for all the students.
Please pardon me, sir. Please pardon me. I could not keep the time.
Okay.
Everyone,
No, sir. That's doesn't matter.
I request the audience to excuse me. Sorry.
Okay, sir. Doesn't matter, sir. Everything will be there. And, it was highly informative, and we are so happy to store it in our YouTube channel. And it was yes, sir. Then I invite Victor to make a reflection on this great, interesting talk. Good, sir.
Thank you, Shajil Mash. It's a very, very exciting time for us. It's not simply exciting talk, an exciting time in this pandemic era. And I am very sure that 100% enjoyment, 100% learning, 100% excitement, every one of us experienced in this hour and a half plus. Of course, we have created a lot of records. This talk itself is a record in terms of time and its excitement. And I thank Mr. Subramanian for preparing so well and delivering such a perfect talk, which made every child realize how complex and how science is embedded in orbit system.
Thank you.
Now,
Thank you, sir.
And now, lot of things have happened in our pandemic time, and we have, in fact, we used to have exciting programs face to face in universities and NIT, etc., etc. But we lost all that, and we thought we lost everything. In February, we made a program in university for 2 days, and at that time I got a call from our PJ Bhatt, our Bhatt, saying that Kuti, it looks Kerala is grappling with Wuhan COVID, and is it appropriate now for you to go ahead with the program? That was a shocking question to me. I didn't know what to do. I immediately contacted Dattan, MC Dattan, who was our director, VSSC director, etc., who was a scientific advisor to Chief Minister here in Kerala. He also told me, Kuti, it looks difficult. It is better you postpone it. Of course, it was on 8th and 9th February, and this talk was happening, I think, on 31st January or so. So then I thought the world is shut behind us, what to do, and then later things have happened. But 23rd May, we started our webinar. It started in a very slow motion, but we could enlist and get exceptionally good scientists from ISRO and elsewhere, and they made the scenario better and better, greener and greener every week. It was a weekly program every week. And then we entered into a quiz in that process, and that turned out to be exceptionally great program. And the webinar, which used to get limited in Malabar area, started spreading to Kerala. Then we found in the quiz, prizes are won by students in Chennai, Karnataka, Madhya Pradesh, and places like that. We started, so it's spreading. Today, the news is that, at Switzerland, a student has won our quiz. So, and then, see, today, the dignitaries who are present in this program, our next month program is by Krishna Priya, your colleague from URSC, and she is present today. And I'm very happy to see her in the participants, and very, very welcome, Krishna Priya Madam. This will give you an idea about how you are going to handle your program on 12th June. 12th June program will be by Krishna Priya. She will be talking on powering the satellites, solar power, and I'm very sure it is going to be an exceptionally good program. Not only that, we have got PJ Bhatt here, Shivaram, Mahadevan, Sundaramurthy, VL Swaminathan, CM Nagrani, Joshi Saab, Nikhil Mugund from Germany, Pappan, Dr. Sundarajan, Dr. Rangarajan, and maybe some more whom I may not have noted. So it's an exciting day for us, and I have an announcement to make. Apart from our June 12th program, that is our usual monthly webinar, we are going to have our anniversary of the webinar series on 23rd May 2021, an anniversary program. That will be a program. Actually, that program I got good inputs and good guidance from Dr. S. Rangarajan. He told me that we will make it a program highlighting what we can expect in the next 50 years in space in terms of technology, in terms of human benefits. So that will be a program of that variety, and that program will be presented mainly by the students. Two students will be making the presentation, and the persons like Dr. Rajan, maybe Batsab, and some more maybe there as our referees or panelists, and we will give a shape to the program soon. So this is a very good occasion. There is hardly any time left. So I wanted to talk about multiple things which we have started doing, but there is hardly any time left there. So I request Shajil Marsh to carry on further with the interaction with the students. We would have liked to listen to our veterans here like PJ Bhatt, Dr. Rangarajan, Sundarajan, etc., etc. But I don't know whether there is any time available. I leave it to Shajil Marsh.
Okay, sir. But anyhow, we want to get some reflection from here. I could see Rangaraj sir is with video and audio. I could see the, and please make a comment on this wonderful talk, sir.
Yeah. Let me make it extremely brief and save you time.
Okay.
It was a very good talk covering from end to end, right from, I listened to the entirety of the 90 minutes and starting from the very fundamental things and then going about it with good figures, equations, and so on. But what impressed me most was quite many times it emphasized what the students should do by keeping their eyes and ears open, look at the data differently from a different angle, and probably something big may come out of that. So that kind of a motivation is very important. It's not like you just go through something which has been already written off and then you pass the examinations, but more than that. And there are several examples, whether it's Tycho Brahe or whether it is more recently Arthur Clarke. So that kind of an approach is very important, and I think it's very much of a motivation for the students. All the very best. Thank you.
Thank you, sir. And PJ Bhatt sir is continuously supporting our students for the past 4 years on these basics, and we want to get some
2016
yes,
onwards, Shajil Marsh.
yes, sir.
2016
for 5 years, he's continuously doing and nurturing our student on this aspect. And I invite PJ Bhatt sir. Welcome, sir.
Thank you, Shajil sir. Subramanian,
Yes, sir.
I felt so proud about you. I
Thank you,
mean,
sir.
it was such an excellent talk. Especially,
Thank you.
as they are telling, I have been going around and giving some talks on orbits. But here, the way you explained, I mean, especially the way in which the students have been told about the concepts of orbital parameters, the perturbations, and other things, the way in which the explanation has come from Dr. Subramanian is something excellent.
Thank
So
you, sir. Thank you.
I'm sure students, I wish there was some time available for him, because the way in which he went on, definitely that caused the time, but the time anyway, there is a limit always. But whatever Subramanian has conveyed about orbits during this period, I'm sure a lot of knowledge which has gone into that. And I second the opinion of Dr. Rangarajan that just looking at things which others have done and going through that and understanding is one part. As Subramanian has put it in his talk twice or thrice during his presentation, he brought out, when he talked about Tycho Brahe or Kepler, he talked about at every stage what he talked about. He brought out this point again and again, that when you look at data, you look at data with inquisitiveness. And I'm sure this team which is here, the US Case Club, the youngsters have the capability to do it. Okay, so these kind of talks, I wish the students take it in the right way. And I am very much pleased to know about announcement made by Kutti sir regarding the future which is coming, where our youngsters are going to come and do the survey, do the study, and they come and present. I am very eager. In fact, I'm more keen to be part of listening to these youngsters. I wish all the best. Subramanian, once again, thank you,
sir. Thank you.
Thank you, sir. And we know a lot of dignitaries are here, and by the time is our limitations, sir. So, with your permission, I invite the eager students are there with their question answer session. I invite Varun and team to deal with these questions. I know a lot of questions will be there. Please come, Varun and team, to handle the question answer session.
Yes, sir. Thank you, sir. Thank you for inviting me. Our friend, our student Ashwati is here for handling the question session. Before moving to the question session, I just want to mention one more point that Shri sir, we didn't announce about our magazine.
Okay, after that, you start with Q&A. After that, we'll discuss. Announce it. Okay.
Okay, sir. Okay. Then now let's move on to the question session. I welcome Ashwati for handling the question session. Ashwati, please.
Okay, thank you, Arnada. Hi, good afternoon to all. It was a wonderful session about orbit dynamics, and thanks to Shri Subramanian sir for setting aside your valuable time for us. And here I got so many questions to ask as usual, and I ask only few for now. Can I ask one by one, sir?
Yes.
The first question is, sir, will the wobble motion of Earth in its orbit affect the orbits of satellites?
Yes, because the orbits of satellites depend on that orbital motion equation, which is dependent on the distance. So the gravitational waves which are caused by this kind of wobble will affect the orbit of the satellite.
Okay, thank you, sir. Can I ask the next one?
Yes.
Next question is, which orbit has most stability and life?
This in a general way we cannot answer that. For example, let us take one particular orbit like geostationary orbit. This geostationary orbit is getting disturbed by a concept called triaxiality of the Earth. So that means when the satellite is over particular longitudes, it will be stable, but when it is at a particular longitudes, it will be unstable. Like for example, you might have heard of a stable equilibrium, neutral equilibrium, unstable equilibrium. So we are actually lucky from India point of view. The longitudes over India, like 74 degrees east longitude, the satellite will be stable. So it depends upon the nature of the orbit.
Thank you, sir. The next question is it possible to reduce the time of 7 months of time to catch orbit of Mars? Is it possible to build a Suez Canal to Mars like a shortcut orbit to Mars?
Yeah, the second part of your question is being thought of by some scientists, but it may take quite a while. But it may happen in future. But the other one, reducing the time taken to reach Mars, So that ultimately it basically it depends on the kind of push which you are trying to give from the Earth. Like in my presentation where I showed the satellite going from Earth to Moon, there are many elliptical orbits around the Earth, and we are always continuously taking the Earth's gravity also as an additional help to push the satellite towards another celestial body. So if that kind of a job can be done by your launch vehicle itself, like some of the space agencies are already doing that, then it will be possible to reach in a lesser time. So it depends upon the kind of push which you are able to give.
Okay, sir.
Varun, can I intervene for a minute? There is some important announcement to be made by Varun about a magazine which we are bringing out. See, at this point, I would also like to highlight, which most of you know, that our program is being managed from conceptual state to execution as it's done today by a group of students like Varun, Sriram, Adil Krishna, etc., etc. So this magazine also is Space Club magazine also being conceptualized and organized by them. So he wanted to make an announcement. Then we will resume the question and answer session, please.
Thank you, sir. Thank you for inviting me. Sorry, Subramanian sir. Sorry for the inconvenience.
No problem. Please go ahead.
We are going to release a magazine, an e-magazine under the UL Space Club on our programs and special themes related to space science. And we are expected to release our e-magazine on the 23rd program, as Kutisa said. On 23rd, we will have a grand program as an anniversary function of our webinar series. On that program, we are expected to release our e-magazine. And our chief editor of our magazine is Dr. K. Jairam sir, former deputy director from ISRO, and he's guiding us. He is one of our mentor, and under him we have an editorial board, and our name of our magazine is Stellar Chronicle. The magazine named as Stellar Chronicle is by UL Space Club, and it will be released on 23rd function. So hope all of you will read, download and read the magazine, and we will have something special in that magazine for all of you, all followers of UL Space Club. Thank you, Kutisa. Thank you for the time.
Okay, sir. Can I ask the next question?
Yeah, yes.
The next question is, what exactly is the time of perigee passage and orbital inclination? Or how do we calculate the satellite's exact motion using time of perigee passage?
Yeah, see, once you know the orbital parameters, given a particular time, you will be able to get the orbital parameters, like what I had said, the Cartesian coordinates, like in the form of Cartesian coordinates x, y, z, x dot, y dot, z dot. From that, you will be able to calculate the distance. So at what particular time the satellite is in which particular region of the orbit, you will be able to find, and you can fix the time at which the satellite is crossing the perigee, which is called as the time of perigee passage. And from that, after a particular instant where the satellite will be again, which is calculated based on the governing laws of motion, can be calculated.
Okay, sir. The next question is asked by Arun Shivaraman, sir. The question is, as per gravity anomaly map, most of the rockets enter the atmosphere over Australia, for example, Skylab. But why this Chinese rocket is expected to fall over New York too? And how is the Chinese rocket debris tracked and predicted to fall tomorrow morning to the Earth?
Yeah, here the prediction of the satellite or the any body's re-entry into the Earth is a bit tricky. So, firstly, what is being done? There are a lot of antennas, ground station antennas, and monitoring equipment spread all over the globe, especially by certain countries. For example, in USA, they have an organization called NORAD, which keeps pointing their antennas on the cosmos, and then they will be able to find where a particular sudden new object or an existing object is orbiting. So, in this particular case of this Chinese launch, some pre-indication was always there. So, the prediction of an orbit is a bit easier in this case because it was already known. But though they may not have told exactly where they are going to put it, to some level of accuracy, it can be known. But the time of re-entry, that is pretty difficult for anyone, because till a particular level, that is till the time of reaching the atmosphere, till that time they will be able to guess fairly precisely. But once that has happened, then the way in which the body is going to split and the way in which the direction it is going to take, that may not be that precise. So, as I said, most of the re-entries are getting into the oceans or seas just because the planet is covered in that way. So that is it is always not perfectly possible to do, but at least a region can be given over which it can be expected, including the time of re-entry is also a bit difficult to guess exactly.
Okay, thank you, sir. That's all for now. And once again, thanks to Subramanian sir for your valuable time.
Thank you very much for all the students.
Oh, thank you, sir.
Sir,
Bernardo, over to you.
there were a few more questions, sir. But we are having a lack of time here, so I would like to cut off the question and session for today. So all of you can ask your questions in our groups or to our mail ID. We will try to find out the answers through our experts. So thanks to all participants. Over to Shail, sir.
Okay, thank you, Varun and team. You have done this question and session wonderful and utilized these great scientists of India, and we'll be ever thankful in these things happen. Today, as Kuti sir mentioned, it's a record day. Total participants were there. We could see a queue of students who are not able to enter in this directly to this platform, but they may be able to see and watch our program through the YouTube channel. So I think it's time to declare about, before we go to the program, we want to declare about the next program, our 23rd May. That's 1 year completion of this webinar series on this pandemic. We are actually designed a program of students. Actually, the students or the student fellows of UL Space Clubs are the backbone of these things. They are the designers and executors, and we elders are only giving an environment for them. And I think Kuti sir will make further more declaration on these things. Welcome, Kuti sir.
Shridilmash, I already said, our first anniversary of this webinar series is coming on 23rd, and we are going to have a program on what the theme will be. What can we expect in the next 50 years in the area of space in terms of conquering Mars, Moon, and other planets, and even colonizing if possible. Maybe all these are possible in the next 50 years, and our students will be trying to understand how the space technology is moving, how the space technology is enriching itself and trying to acquire the resources of the world for the benefit of mankind. So they will be presenting a program on that. We have not worked out the final measure of that. I have talked to Dr. Rangarajan about it, and he has come out enthusiastically about an idea on that. So we will come out with the idea. So 23rd, you can expect at this time at 3 p.m. a program, the details of which will be announcing shortly. And as I said, next month program, normal webinar of the June will be on 12th June on power systems in satellites and orbital platforms by Krishna Priya of UR Rao Space Center, Satellite Center, Bangalore. Thank you.
Oh, thank you, good sir, for this credible information to our participants. And next is our the UL Space Quiz program. That's the main attraction of these things. I think Varun will make an announcement on this pasting of that link. Varun.
Yes, sir. We have pasted the we have posted our webinar quiz link in the chat window. Student Nandana has posted the webinar quiz link in the chat window. You can access the quiz link only after the vote of thanks of this webinar session. So please attend the all questions. There are 7 questions. Attend the maximum number of questions, and all questions will have 5 marks each. So the faster and the accurate answers will be considered for the prize.
Okay, thank you, Varun. Thank you, Varun. And today we are concluding this great event and great informative program we ever conducted, and it's a concluding ceremony. And I invite Adil, the student fellow of UL Space Club, to express vote of thanks on behalf of UL Space Club and ULCCS. Welcome, Adil.
Thank you, Shri. Thank you for inviting me for the vote of thanks. We are really honored and so lucky to hear this talk by this veteran scientist from URO Satellite Center on this occasion of 36th session of US Space Club webinar series. The session was really great, well organized, and engaging to hear about one of the key things which facilitated our space curiosity fly beyond the solar system. We are extremely thankful to Subramanian sir for this enlightening session on orbit dynamics. I am very thankful to everyone gathered here as we complete the 36th session of this special program. And it's astonishing to think about that we started this journey a year ago this month. And I would like to mention, we are always happy that along with these students, many eminent personalities are always with us in these webinars as a family. And I thank all of those veterans for such a great cooperation, engagement, and guidance they offer. I thank all the participants, including students, teachers, and all others. Also, I thank our chief mentor, E.K. Kuti sir, moderator Shajil UK sir, and all students, fellows of the Space Club. Thank you.
Thank you, Adil. And now we are happily concluding these sessions. Okay, thank you.
Thank you. Thank you.
Hello. Krishna Priya madam is there?
Thank you, sir.
He was present some time back. Okay. Okay, but sir. So
Yes, sir.
hello, madam. Here. Oh, very nice. Very nice. You have been throughout. I saw you in the beginning itself, and you have been throughout. It is so nice of you to spend so much time.
It was a nice lecture, sir. I was very much interested, and so I continued.
Oh, so nice. Excellent. Excellent. So on 12th